In this video, we're going to look at parametric differentiation. Now, parametric differentiation is quite simply differentiating equations which are given in parametric form. So we're going to jump straight to the examples and get started on how we go about doing this. Okay, so the first example says if x is equal to at squared and y is equal to 2at, find dy by dx. Now, to do this, this is what we're going to be doing here. We're going to say dy by dx, that's what we're looking to find, and we're going to be using the chain rule to do this. So it's going to be dy by dt, dy by dt times dt by dx. So what we need to do in this is we need to find our dy by dt, we need to find our dy by dt, and we need to find our dx by dt. We need to find our dx by dt. So dy by dt, your y is equal to 2at. So you can differentiate y with respect to t to find your dy by dt. So differentiate your y with respect to t, you're going to be left with 2a. Same idea. To find dx by dt, differentiate this x with respect to t. And if you differentiate at squared with respect to t, you're going to get 2at. So that means dy by dx, is equal to 2a, and then times, so just on this, we need to find dt by dx is going to be 1 over 2at. So it's going to be so dy by dx, this was my dy by dt. Now I'm going to find my dt by dx, which was, we've just said, is 1 over 2at. So all we do is a wee bit of cancelling out. That's going to be 2a over 2at, and then that just cancels down. 2a and the 2a cancel out, just leaving you 1 over t, and that's it done. So just to go over that again, first of all, we're going to use our chain rule. I would just write this down. Every time I was doing this question, I'd write it down. Dy by dx is equal to dy by dt times dt by dx. And you can find dy by dt. So that's just differentiating your y term with respect to t, differentiating your x term with respect to t. And then remember, if dx by dt is equal to this, then dt by dx is a reciprocal of it. And then just fire your dy, that's my dy by dt, and that's my dt by dx. And then if it cancels down, as it did in this case, make sure you do that as well. Okay, this next example, I have filled it in because this pen is playing up and won't seem to work today. So here we've got dy by dx is equal to, we're to find dy by dx, you're told x is equal to 3 over t, y is equal to the square root of 1 plus t squared. First thing I've done here is I've rewritten my x and my y in index form. So x is equal to 3t to the minus 1, and y is equal to brackets 1 plus t squared, and that is to the power of 1/2. I've done this so that I can differentiate them. So my dx by dt, x differentiate with respect to t gives me minus 3t to the minus 2. And I'll write it back in this form. So get it out of index form again, and then you'll see why in a wee bit. Makes it a lot easier to work with. So I have minus 3 times t, minus 3 over t squared, and therefore dt by dx, which I will need, will be minus t squared over 3. So just reciprocal that to get from your dx by dt, turn it upside down to get to dt by dx. Okay, your dy by dt is a wee bit trickier. It's a function of a function. So differentiate with respect to this bracket, bring your half down, multiply by your half, then reduce your half by 1, so it goes down to minus 1/2. Keep what's inside the bracket the same. Then differentiate inside the bracket, which would be 2t. So 2t times 1/2 is just t, so it's t upon brackets 1 plus t squared to the power of minus 1/2, which is the same as t over 1 plus t squared to the power of 1/2. Okay, write down your chain rule. It was dy by dx is equal to dy by dt times dt by dx. There's your dy by dt, there's your dt by dx. And then just multiply along the top, you'll have minus t cubed. Multiply along the bottom, you'll have 3 upon 1 plus t squared, all to the power of 1/2. Okay, the best thing in this example is, the most important bit in this example, I should say, is writing this in index form at the start. If you don't and you try to differentiate that without doing it, without putting an index form, it gets very complicated. It's very tricky. You're doing it far too much, trying to do far too much in your head. So write your x and your y terms in index form, and then just set all your steps out clearly, and it's not too difficult an example. Okay, in this example it says find the equation of the tangent at the point P where t is equal to pi over 4 on the curve defined parametrically by x equals 2 cos t minus cos 2t, y is equal to sine t minus sine 2t. So we're using a combination of our parametric differentiation and also differentiating trig. First thing we want to do is sub in your value of t into both the x equation and the y equation to give you your coordinate on our tangent, on our curve. So when x equals pi over 4, you just sub that in, so it's 2 cos of pi over 4 minus cos. 2 times pi over 4 is pi over 2. And if you hit that into your calculator, make sure it's in radians mode, you'll get an exact value of root 2. Leave it as this exact value and you'll see how nicely it works out if you do that. Same idea, put pi over 4 into as your t value into y. So it's 2 sine pi over 4 minus sine of pi over 2. And again, put that into your calculator and it should come out as minus 1 plus root 2. So it's an exact value. So the coordinate we're going to be talking about is root 2 minus 1 plus root 2. Okay, it talks about tangents. That means you've got to differentiate find dy by dx. So you need to find dx by dt and dy by dt. So differentiating your x with respect to t, you will get minus 2 sine t plus 2 sine 2t. Differentiate your y with respect to t, you'll get 2 cos t minus 2 cos 2t. So then write down your chain rule for parametric differentiation. Dy by dt is equal to dy by dx, is equal to dy by dt times dt by dx. So that's your dy by dt times 1 over your dx by dt, which works out as this function. So its top line is 2 cos t minus 2 cos 2t, bottom line is minus 2 sine t plus 2 sine 2t. So when or at t is equal to pi over 4, and I've just put that into your equation. Did this all on my calculator, obviously, just put that in, and then what I got as my exact value for my gradient is 1 plus root 2. So what I've got so far is I've got my coordinates with the x value and the y value, and I've got the gradient. So my tangent is y is equal to, this is my y equals mx plus c equation, and my m, my gradient, we've just worked it out, is 1 plus root 2. So now what we want to do, we need to find this value of c. So to do this, you're going to sub in your coordinate. So your x value is root 2, and your y value is minus 1 plus root 2. So instead of writing y, you write minus 1 plus root 2. Instead of writing x, you write root 2. Multiply out this bit. 1 times root 2 is root 2. Root 2 times root 2 is 2. And then bring all of this stuff across this side. You'll have 1 minus 2, which is minus 3. You'll have root 2 minus root 2, which cancels out. So you're just left with minus 3 is equal to your c. So you find everything, just make sure you write your tangent out. So just say, therefore, your tangent is y is equal to brackets 1 plus root 2 upon x, then minus 3, and that's it done. Okay, we're now going to look at finding d2y by dx squared using parametric equations. So if we think back to what d2y by dx squared is, it's your dy by dx differentiated again with respect to x. So more often than not, your dy by dx term was in terms of t, so you can't differentiate directly with respect to x. So what you could do is differentiate it with respect to t, and then multiply by dt by dx. So if you imagine that dt cancels out with that dt, just leaving you the derivative of dy by dx differentiated with respect to x. So to do it, basically what you want to do is differentiate your dy by dx with respect to t, and then multiply by dt by dx. And if you've set your work out well, you will already have in your working out dt by dx. Okay, I'm going to work through this example and see how we do this. So in this example, the first thing I'm going to do is just rewrite my x and my y in index form first of all. So there's my x in index form, and I will just then differentiate it to see what I get. So I'm just going to get minus t to the minus 2. Now I'm just going to write that, take that out of index form again. That's me minus 1 over t squared. And the reason I'm doing that is so that I can say what my, therefore my dt by dx term is. So my dt by dx term is going to equal to minus t squared over 1. We'll just leave it as that, minus t squared over 1. My y term in index form is going to be t plus t to the minus 1. So dy by dt is going to be equal to 1 minus t to the minus 2. And I'll just leave it as that way for that one. Okay, what we want to find then is dy by dx. So dy by dx, remember, is dy by dt times dt by dx. And then if we put both of those things in, my dy by dt was 1 minus t to the minus 2. And then times, and my dt by dx is just going to be minus t squared. So we can just multiply this out and see what we get. You're going to get, so you're going to get 1 times minus t squared is going to be minus t squared. And then minus t to the minus 2 times minus 1 is going to be times minus t squared, sorry, it's going to be plus 1. Sorry, that was my minus t to the minus 2 times minus t squared. That will just give you plus 1. Okay, that's what you've got so far. So that's my dy by dx. Okay, the next thing I need to do is differentiate my dy by dx with respect to t. So I'm differentiating my dy by dx with respect to t. So if I do that, differentiate your dy by dx with respect to t, in this case, I'm going to get minus 2t. I'm just going to write down my formula if I want to find my d2y by dx squared. It is equal to the derivative of my dy by dx, and that's with respect to t, times my dt by dx. Okay, and in this case then, that's going to be minus 2t times, and my dt by dx, I've written that over here, my dt by dx was minus t squared. I've written as minus t squared over 1, just for think of it, that's just minus t squared. So times minus t squared, which is just going to be 2t cubed, and that's it done. Okay, I've written the solution out for this next example again. It says find and classify the stationary points on the curve with parametric equations x equals t squared plus 4 and y is equal to t cubed minus 12t. So the first thing we've got to do, if it says stationary points, is you've got to find your dy by dx. So find your dx by dt, it was 2t, and then do the reciprocal of that, so dt by dx is 1 over 2t. Your dy by dt is 3t squared minus 12. So this is your dy by dx, so this is dy by dt times dt by dx, which gives you 3t squared minus 12 all over 2t. So at a stationary point, dy by dx equals 0, so that's why you put dy by dx equals 0. And if you have a quotient, which is just a fraction, a quotient is equal to 0 when the top line is equal to 0. So just put 3t squared minus 12 equal to 0, which gives you 3t squared equals 12, which gives you t squared equals 4, which gives t is equal to plus or minus 2. So there's two values here, and we'll see why. Okay, we want to then differentiate your dy by dx. So just written down my dy by dx, and we're going to differentiate with respect to t. So it's a quotient, so we're using the quotient rule. So the top line is your u, the bottom line is your v, and you can see I've differentiated them both to give you du by dt and dv by dt. Write down your formula then. So this is us differentiating your dy by dx with respect to t. So it's v du by dt minus u dv by dt all over v squared. I've subbed all of that in. You can see that's my v, my du by dt, my u, my dv by dt, and that's my v, and it gets squared. And I did that, and I got 6t squared plus 24 all over 4t squared. If I go on down, my dy by dx, d2y by dx, I should say, this is my dy by dx differential with respect to t multiplied by dt by dx. So it tallies up. So this is my d2y by dx squared. I always think of it as my testing function to see if something is a maximum or a minimum. So what we're going to have to do now is sub in my t values, which were t equals 2 and t equals minus 2, into this and see if they're positive or negative. So when t is equal to 2, when you sub t equals 2 into your d2y by dx squared, you got 3/4, which is greater than 0, therefore it's a minimum turning point. When t is equal to minus 2, you subbed it into d2y by dx squared, and you got minus 3/4, which is less than 0, therefore it's a maximum turning point. So we know there's maximum, minimum turning points, but we actually don't add certain t values, but we don't know what the real coordinates are in terms of x and y. So we've still got to find those. So when t equals 2, sub t equals 2 into your original x and y, and you'll get x equals 8, pardon me, and y equals minus 16. So that tells you that 8 minus 16 is a minimum turning point. Same idea, when t is equal to minus 2, sub that into your original x and y, and you get x equals 8 and y equals 16. So 8, 16 is also a maximum turning point. So read the question, find and classify the stationary points. We found our stationary points are 8 minus 16 and 8, 16. And 8 minus 16 is a minimum turning point, 8, 16 is a maximum turning point. So we're happy we've answered the question. Okay, the last example for us to do for this differentiation section says given that x is equal to sine theta and y is equal to 2 cos theta, and part 1 I've just done out so far, it says show that dy by dx is equal to minus 2 tan theta. So dx, the first thing you're going to do is differentiate your x with respect to theta and your y with respect to theta. dx by d theta is equal to cos theta, therefore d theta by dx is the reciprocal of that, so 1 over cos theta. And differentiate your y with respect to theta, you'll get minus 2 sine theta. So dy by dx, this is my dy by d theta times my d theta by dx. So it's minus 2 sine theta over cos theta, which is the same as minus 2 tan theta. Okay, for part 2 it says hence show that d2y by dx squared plus 16 over y cubed is equal to 0. So the first thing we've got to do is find this d2y by dx squared. So to do that, I've just written down a formula. d2y by dx squared is equal to the derivative differentiating dy by dx with respect to theta, then multiply by d theta by dx. So the first thing I'm going to do is differentiate dy by dx with respect to theta. Here's your dy by dx, it's minus 2 tan theta. From your differentiation of trig notes, you should know if you differentiate tan, you get sec squared. So differentiate minus 2 tan theta, you'll get minus 2 sec squared theta. Sub that into this equation, so that's minus 2 sec squared, and your d theta by dx was 1 over cos theta. So sec squared is 1 over cos squared, so that's minus 2 over cos squared times 1 over cos squared, which is minus 2 over cos cubed. All we've got to do now is just investigate this thing, and the way you set this out is important. Just set out the left hand side, so this is my left hand side equals, so don't say at the minute that this is equal to 0. That's what we're trying to prove. So this is just d2y by dx squared plus 16 over y cubed equals minus 2 over cos cubed theta plus 16 over, and that's my y, 2 cos theta, and that's all cubed. Cube the 2 cos theta, you'll get 8 cos cubed. So then, and then tidy the 16 over 8 cos cubed up, you'll get 2 over cos cubed theta. So we have minus 2 over cos cubed theta plus 2 over cos cubed theta, which just cancels out to give you 0. As required, and that's it. You have done the example, completed the example. Okay, so the important thing is don't say at this stage that this is equal to 0. Just investigate the left hand side, and then it's like the big reveal at the end. It is equal to 0, so you've solved it. You've got what you need. Okay, you're now ready to do the last wee set of questions on this. So it's topic 6, differentiation B, exercise 3 and exercise 4. Forget about exercise 5 at the minute. That's a homework exercise.